Alright, today we are going to start talking about the Pythagorean theorem. We're going to start talking about the Pythagorean theorem. Right? Hopefully we all know by now what the Pythagorean theorem is. Right? A squared plus b squared equals c squared. And this relates the three sides of a right triangle, right? Where A and B are the two legs, and C is the hypotenuse. So all the time, if we take the square of this side plus the square of this side, that will equal the square of this side. So literally, what that's saying is if we take the area of a square, so if I make a square out of this side, I make a square out of this side, and I make a square out of this side, this area plus this area equals that area for every right triangle, no matter what. Right? So since you guys are the honors class, we're going to take a look at a proof of the Pythagorean theorem to start. And then we will look at some practice problems here. Alright? So we're going to take a look at a proof by Salcon. There are actually a bunch of different ways to prove the Pythagorean theorem. This is just one of them. You will never have to reproduce this on a test or anything, but it could be like a bonus question or something. Okay? So here is a proof of the Pythagorean theorem.
We've already seen several videos where we wonder what the Pythagorean theorem is and how it can be applied to find the sides of right triangles and even to find the distances between points on the Cartesian planes. Pythagorean theorem. And just as a review, it tells us that if I have a right triangle, and if C is the side up the right angle, right? That's my right angle. C is that side. It's the longest side. We call that the hypotenuse. Hypotenuse. Then the square of the other sides, the sum of the squares of the other side will equal to C squared. This side is A, this side is B. The Pythagorean theorem tells us that A squared plus B squared is going to be equal to C squared. We did several problems where we used to solve different triangles. What I want to show you in this video is really a visual, you can view it as a visual proof of the Pythagorean theorem. To see why this actually makes sense. To understand that, I'm going to draw a little bit of a diagram. Let's draw a little right triangle here. Let's say that that is my right triangle. And let's say that this is A, this is B, that is my right angle. That right there, this right here, that length right there is C. Now, what I'm going to do is draw this exact same triangle, but I'm going to rotate it a little bit. You're going to see what I'm talking about. This right here is the exact same triangle that I just drew, except I rotated it. This is A, this is B, now this is C. This is the exact, you could do this, you could take a ruler out and actually do it in the A, B, and C, and you can actually you just rotate this triangle around to the right like this, just rotate it like that, and you get this triangle right just like that. Now I'm going to rotate it again. I'm going to rotate it again. And I'm just going to imagine copy and pasting it. And then I will get this triangle. I will get that triangle. Just like that. Once again, this is A. This is B. And this is C. These triangles are all the exact same triangle, the exact same measure. Now let me rotate this again. And I'll get this triangle. I will get this triangle right here. Once again, this is A. This length right here is A. This length right here is B. And this is the hypotenuse of this triangle. This is C. Now, what do we have here? We have all of these right angles, and inside I have this other square that is inscribed into this right angle. I can prove to you, if you like, that these are also right angles. And why don't I just show it to you? You may or may not already hear that the angles in a triangle add up to 180. So if you call this angle x, you call this angle y, we know that x plus y plus 90 degrees have to be equal to 180. So x plus y plus 90 have to be equal to 180. Or you could say that if you subtract 90 from both sides of this equation, x plus y are going to be equal to 90. I just subtracted 90 from both sides. This disappears. 180 minus 90 is 90. And this x and y, they're all over. If this angle is x right here, so is this angle. This is the exact same triangle, so is this angle. So is this angle. If this angle is y, so is that angle, so is that angle, so is that angle. Now, you may already, or may not already know, that if you have three angles that form a line, if you have three angles that form a line like this, so let's say we have angle A, angle B, and angle B, and angle C, just like that, and together they kind of form you could imagine a semicircle, or they go from one line all the way back, then A, B plus C are going to be equal to 180. A plus B plus C is going to be equal to 180 degrees. They complete a 180 degree arc. Now, if you look at, let's say, this point right here on our diagram, you can see that angle x plus this angle right here, I'll just call it, what should I call it? I can call it angle Z. X plus Z plus Y is going to be equal to 180 degrees. They form a line. So x plus Z plus Y, or maybe I should write it as x plus Y plus Z is equal to 180. Now we already know that x plus Y is equal to 90. So this is equal to 90. So 90 plus Z is equal to 180. Z minus, well, both sides of this equation minus 90 degrees. You get 180 minus 90. Subtracting 90 from both sides. So Z is equal to 90 degrees. So this is definitely, these are all 90 degree angles. Inside, their sides are all the same length of C. So this is a square in the middle of this diagram. Now, let's think a little bit about what the area of the square is. And there's two ways we can come up with the area of that square. So the first easy way to think of the area of the square was a square. This length is C, that length is C. To figure out the area, I just meant one side by the other side. It's C times C, or C squared. I want the area of that right there. It is C squared. C times C area is equal to C squared. But how else could we figure out that area? Well, we could say, well, it's also, that would be the area of this larger square, of this whole square over here, right? Minus the area of these triangles. That also would give us the area of that inside square. So what is the area of this outside bigger square? Well, each of its sides are a plus b, and so you take a plus b. If you want the area, you can say a plus b times a plus b, or a plus b squared, right? That's the area of the outer square. But we still have to get the area of our inner square, area of small square. We still have to subtract out the area of these triangles. What are the areas of these triangles? Well, the area of each of them, we have to subtract out. The area of each of them is 1/2 times base times height, or base times height, AB. 1/2 AB. That's how big, that's the area of each of these triangles. Now we have 1, 2, 3, 4 of these triangles. So it's 4 times 1/2 AB. This is another way of getting the area of this inside smaller square. Now let's just do a little bit of algebra. We're pretty familiar with this. To essentially simplify the right-hand side of this equation right here. So a plus b times a plus b, a times a is a squared plus 2ab plus b squared. Then we have minus, what do we have right here? Minus 2ab, right? 4 times 1 half is 2. So minus 2ab. Well, these cancel out. 2ab minus 2ab, we're just left with a squared and b squared. So the area of this inside circle, which is c squared, is also equal to a squared plus b squared. And I've just shown you a visual proof for the Pythagorean theorem. Because remember, a and b were the smaller sides of a right triangle having c as its hypotenuse. And from there, we constructed this bigger diagram. Hopefully you found that fun.
So, just an example of a proof of the Pythagorean theorem. Alright, there are a lot more proofs, but that is, I think, the simplest, most straightforward one. So let's
I forget his name. We had to have this whole math history class. Don't get it.
Pythagoras.
Yeah, that's who it was.
Yes, that's his name. Alright, so let's now take a look at a few practice problems solving for missing sides in right triangles. Okay? We just proved this relation. Okay? A squared plus b squared equals c squared, where a and b are the two legs of a right triangle. Right? That's really the only part that students mess up sometimes. Right? These a and b are the legs, and c is the hypotenuse. Okay? Which one's A and which one's B doesn't matter. These in there. Not coming. And then C always has to be the hypotenuse. Okay? So in this first example, we're missing one of the legs. So this side would be B, this side would be C. My setup would be A squared plus 12 squared equals 13 squared. Then I can square those values. 12 squared is 144. 13 squared is 169. Subtract the 144 over. Yep, we get a squared equals 25. And then the final step, to get rid of this square, we need to take the square root of both sides. And that'll be 5. Square root of 25 is exactly 5. Okay? We okay with that process? Now, technically, when we take a square root, we would get a positive and a negative value, right? The square root of 25, yeah, is actually positive 5 and negative 5. However, in this situation, we're talking about a length. So a length is always positive, right? So we just don't include the negative, except we're missing the hypotenuse. So in this case, my setup would be 20 squared plus 30 squared equals c squared. 20 and 30 are the two legs. So 20 squared is 400. 30 squared is 900. So we get 1300 equals c squared. Then we can take the square root of both sides. The square root of 1300 isn't a nice number, right? 1300 isn't a perfect square. So we're going to practice simplifying radicals again. Okay, we did the beginning of the year. Right? So we're going to come back to that now. Okay? So if you remember, goal when we're simplifying a radical is to find the largest fixed square that divides evenly into this value. Okay? So we kind of need to know our list of perfect squares to do that. Right? We've got 1, 4, 9, 25, 36, 49, 64, 81, 100, 4, 169, 196, 225. That's the first. Yeah. So here. So we're looking for the largest of these that divides evenly into 1300. Right? This one hopefully is fairly obvious. Right? 100 is going to be the largest one that divides evenly into 1300, but it's not always going to be that obvious. Right? You may have to use the calculator, checking and seeing what numbers divide evenly into that.
What, 16?
I stopped at 15. So, yeah, what is 16 squared?
Yeah, I'm talking about 4.
Oh, yes. Thank you. Forgot one. I went straight from 3 squared to 5 squared. So, to simplify this then, what I can do is split this up into the square root of 100 times the square root of 13. And if I divide 1300 by 100, I would have 13 left over. And then the reason that we do that is now I can take the square root of 100. Okay, the square root of 100 is 10. So I can write this as 10 times the square root of 13. Right. So we're just looking for the largest perfect square that we divide evenly into that. Okay, and that's only if we get an ugly number like this. Here it works out to be a perfect value. So final answer is 10 times the square root of 13. You okay with something like that? Alright, let's take a couple of minutes then and have you guys try a few of these down below here, including coming back to a rhombus here. One of our properties of a rhombus was that diagonals, also that forms right angles. Plus, we get right triangles. So let's take a couple of minutes and try a few of these.
So, with 18, because this one is 18, would it be for 2 squared?
Because we want exact, we're going to do a simplifying thing like we just did. So you get like radical 2, and then you get radical 9, which will get into 3 radical.
Wait, so simplify. Diagonal 18, and then how do you get that?
I don't know.
You just want to see what 2 numbers go in there.
I like that.
You want a number that has like, what do I want to call it, like a base.
Like a perfect number.
Yeah, just like 9 will go to 3, which is,
So 9 comes to 18, because we don't do that for that part.
well, you want radical 2, right?
Well, yeah, but like if you just do that, you don't need it. And then You just put that into square state. Okay. So like 1, 2, it would be two, 225
We're going with the Pythagorean theorem. A squared plus B squared equals C squared. Oh, yeah, you told me. It depends on which one is this. If you're missing A or B, that drags. So if you want to solve for A squared, right, you would subtract the B squared over and say A squared equals C squared minus B squared. Right, you could write this as negative B squared plus C squared, right? It doesn't matter.
4,220.
Right, right.
plus 25 squared.
Well, you would be subtracting. Like if you're solving for one of these, you would be
And what's
subtracting over. So you would write it
25
as
minus
C squared minus the other one squared.
And then I put it into wait, is that what?
No. Yes, it is on Spanish. It'd be, 60. I don't know. Why is it something? Yeah, I knew there was something wrong.
What's 4? Why did you equate them?
Yeah, it's 16 over 81.
16 over 80. Oh wait, we just square both sides. Yeah, okay.
I don't like
Which one? 4?
Why don't we just do
What's up?
It'd just be 9 over 81.
that's it.
Which equals to 1.
These might actually not be that
Yeah, but then if square is.
Yeah.
What is 1 over 9 squared?
It's just 1 over 3. I can do
makes sense. But
I said I can deal with
no. What is 16 squared?
Yeah, I think for number
It's
5.
32 squared?
Yeah, I think that can't be simplified. I think that's just your answer.
It's 1080. 13.
I don't think that's a square. Is it?
You can find that.
No.
Alright. Take a look up here at the answers. Okay, I think number 1 is actually the only one where we could simplify the radical, make it 3 square root of 2. 2, 3, and 4 all work out to perfect numbers, to nice numbers. And then 5 and 6, I don't think that those radicals simplify at all. I know for sure 5 doesn't. I didn't get to check all the numbers on 6, but I don't think it does. So, any questions on So, any questions on solving for missing sides in a right triangle? Well, if it's not a right triangle, we would have to use things called the law of sines or the law of cosines, which we're not getting into in this class. That's something you'll see in pre-calc. No, not really, actually. I mean, we are actually ahead of base. We might have time to do it here at the end of the chapter. So we'll do Pythagorean theorem today and the converse tomorrow. Then we'll get into trig. So we'll do sine, cosine, tangent right after that. And then we may have time to talk about law of sines and law of cosines right after that. We'll see. So we do have one final idea for today. Okay, the 3 problems at the bottom say use a Pythagorean triple to solve for x. Okay, now you can always just use the Pythagorean. If you don't remember your Pythagorean triples, you can solve each of these using the Pythagorean theorem. However, if you remember these Pythagorean triples, you can see are whole numbers. Okay, so there are actually an infinite number of Pythagorean triples. We're just going to focus on the first few of them. So, infinite. So, 3, 4, 5 is the smallest Pythagorean triple. Okay, 3 squared plus 4 squared equals 5 squared. Right. So, we're just going to look at a few of them, but write these lists down here. The next smallest one is 5, 12, 13. 5 squared plus 12 squared equals 13 squared. We actually did this one in one of the examples. Then 8, 15, 17. What's confusing? Yeah, I just have them memorized. These are Pythagorean triples, right? Sets of whole numbers that satisfy the Pythagorean theorem. So it's 7 squared plus 24 squared equals 25 squared.
Yeah, like what is this applying for though?
So
Number 7. Number 7 will be 15 because there's 8 and 7. So 8 squared plus 2
It's
squared.
just easier. It's something that you're-
Exactly. Right? So if you know this list, then you don't have to do any work. You can just look at this right triangle and say, well, I know a Pythagorean triple is 8, 15, 17.
We're not gonna do more work.
If it's a Pythagorean triple and you recognize that, nope. Right? So just looking at this triangle, I know that this missing side is 15. Right? If we know this list of Pythagorean triples. Now, like I said, there's an infinite number of these. We're just going to focus on a few of the smaller ones. Right? Now, this list also includes all the multiples. So if I were to take 3, 4, 5 and multiply every single one of those numbers by 2, I would get 6, 8, 10. That's another Pythagorean triple. If I took all of these numbers and multiplied by 3, I would have 9, 12, 15. That's another Pythagorean triple. Okay? I can do that for any of these. I can multiply every number by some constant to get another Pythagorean triple. So that's what's happening in these next 2 problems here. These are multiples of one of these.
Can you use any number for the multiplying or resolve?
Yep, you can use any number as long as they're the same. So I can multiply each of these by 1,000, right? And get another Pythagorean triple, 5,000, 12,000, 13,000.
So number 9 would be 100 because 7 times 4 is 96.
Exactly. So the idea, if I recognize both of these numbers are divisible by 4, right? So if I divide by 4, divide by 4, we would get that this side, this is 7, and this is 24. So that fits this Pythagorean triple. Right? 4. So this side then would be 25 times 4. Since I divided both of these sides by 4 to recognize this Pythagorean triple. This side less, it would be 25 times 4, or 100. Right? Now, if you don't like that method, you can always use Pythagorean theorem. Okay? That will always work to find a missing side. It's just if you recognize a Pythagorean triple, it could save you a little bit of work. Okay? That's all this is at the end here. And so what Pythagorean triple would number 8 be here?
The 8, 15, 17.
This would actually be another 8, 15, 17. I could divide both of these sides by 3. If I divide 45 by 3, it would be 15. If I divide 24 by 3, that would be 8. So that means this side would be 17 times 3, would be 51. Right? But if you don't like that method, you could always set this up as 45 squared plus 24 squared equals c squared and solve using the Pythagorean theorem. Okay? Just if you recognize a Pythagorean triple, save you some work. Yeah. All right. Questions?
Wow, what a short class.